Welcome to our presentation of Sniffer, a novel model type detection system against machine learning at the SWISE platforms published in VLDB 2023 demo track. This work is completed by Xidian University, Chongqing University of Posts and Telecommunications, and Peking University together. With the growth of cloud computing, MLAS is taking almost every industry by storm, such as healthcare and manufacturing. This is the basic framework of MLAS. Users can access them by only uploading the sample through the black box interface, and then obtain the prediction result without intensive computational resources. The advantage is obvious. MLAS provides a simple and convenient way to access machine learning. Here are some main MLAS providers: Google AI, Amazon SageMaker, Aliyun, Tengxun Cloud, Huawei Model Arts. However, MLAS faces many attacks, threatening the data assets, mainly models or training data. The most representative work is model extraction attacks, stealing the model from the cloud, like this. Another work is membership inference attacks. It can help the adversary determine whether a certain sample is in the training dataset or not. The author claims that there are some constraints for those attacks to achieve great performance. So we summarize the exciting MLAS attacks and the prior knowledge they require, like this. Knowing the model type is essential knowledge for a successful attack. We call them model type sensitive attacks. The fact is that most mainstream real-world platforms do not provide model type information to the user. However, there is no discussion about how to detect the model type of the target model and make MLAS attacks greater again. So we propose a model type detection system called Sniffer to obtain model type with many more query budgets. The workflow of Sniffer is: first, generator synthesizes unlabeled attack samples according to the needs of probes. Second, queries automatically interact with the MLAS platform to obtain predictions of the attack samples and put them in the attack pools. Third, each probe outputs whether the target model belongs to a certain model type. Fourth, in Arsenal, according to the detection result, an appropriate MLAS attack is selected. In detail, probe consists of decision tree probe, models with a nonlinear kernel probe, linear model probe, and neural network probe, which covers the scope of the most state-of-the-art MLAS attacks and common machine learning model types. In addition, the probe modular is totally pluggable. Specifically, Sniffer determines decision tree by discreteness test. We observe that the decision tree's output space is a finite discrete set. The algorithm is that, given a fixed interval S, the prediction sample returned by querier is y prime if y prime is the same as y. DT-probe considers this feature to have discrete properties within this interval. For models with nonlinear kernel, the key observation is after one feature exceeding a huge number, the rate of change of the prediction result plummets. The algorithm is that, given a huge number h, two input data points xi plus h, xi plus h plus p, where p is a minor perturbation. If y prime is close to y, Sniffer outputs km. For linear model, parameters omega and b can be solved through Cn plus c input-output results. Therefore, Sniffer answers whether the input-output equations is solvable or not. For neural network model, adversarial samples are characterized by the fact that the more similar between two model structures, the high transferability. Therefore, Sniffer tests the transferability of adversary sample to decide which neural network type it is. In this demonstration, we show a web-based UI of Sniffer. The main functional interfaces are shown in the picture. In the following, I will introduce our system and demonstration, including how to deploy Sniffer and options for user interactions. The source code and other artifacts of Sniffer have been made available at GitHub. I will introduce the system setup process in the following. First, the audience needs to install a Python environment, which includes some common toolkits, such as sklearn and PyTorch. See document requirements.txt for detailed information. Notably, the predictive interfaces provided by MLAS platforms need to be installed, such as Google API Client for Google. Next, the audience needs to install PHP and build a database. We have exported the structure of database required for Sniffer to the document dbdump.sql, and the audience can import it with a single click. Last, the audience modifies the user-friendly JSON document configuration.json to adapt the system to the deployment environment. For example, it contains the directory of Python environment and the information of database. Once the above configurations are completed, the audience enters the main interface of Sniffer by opening the file main.html. Next, we will introduce the user interactions in Sniffer. After logging into Sniffer, the audience chooses the target. MLAS platform is used to detect the model type against MLAS, while the audience tests the algorithm locally in local simulation. We start by choosing the MLAS platform attack function. First, the audience specifies the experiment name, such as demo. Second, the audience selects the MLAS cloud to be attacked and the prediction API of the target model provided by MLAS platform. In this demonstration, we take the Huawei Cloud as an example, where SVM, which belongs to the kernel model, has been deployed in advance. So we select Huawei Cloud and fill the model prediction API. Since access to MLAS is time-consuming, in order to get the final detection result as fast as possible, Sniffer allows the audience to choose which model types to probe. For example, we check decision tree, kernel model, and linear model in this case. Next, the audience should tell Sniffer about the legal input for MLAS platform. For convenience, Sniffer built in several datasets, which can be selected directly if the target model supports them. Alternatively, the audience can input manually. For example, the Minist dataset can be represented as 28 for feature shape and or -1 for feature range. In this demonstration, we choose a tag dataset as iris. After filling up the above contents, the audience clicks a tag button to launch the attack. When Sniffer is finished, the page shows the processing log and the results. For example, the detailed data points after adding perturbations in GT and KM probe. Moreover, the final results are shown in pie and bar charts. Local simulation allows the audience to choose built-in models or upload a model trained by themselves to test the algorithm. The rest of the interactions are similar to MLAS platform attack. Sniffer provides a query function of the attack history, which can be viewed by clicking Attack History. On this page, the parameters and results of attacks are recorded in detail for review. Thank you.